All right. Thank you, Lynn. Our closing keynote speaker is the quintessential researcher builder. His research lab in Berkeley has produced some of the most popular open source projects, including Apache Spark, Ray, VLLM, and tools like LMArena. And he's also the executive chair of both Databricks and Anyscale. So please welcome to the stage Ion Stoica of UC Berkeley.
Hello, everyone. Very glad to be here. So, and I know that I am the person between the lunch from here, and I'll try to be quick. So today, I'm going to make the argument that arguably the biggest challenge, biggest barrier to AI adoption, in particular in enterprises, is reliability. So what is reliability? According to the NIST definition, is the ability of a system or component to function under stated condition for a specified period of time. What are the properties of the reliable systems? Some of them are accuracy and correctness, obviously, consistency, predictability, robustness, safety. I am not the only one to say that. It was, or the first one to say that. This was a theme over the past few years. This is a paper coming out of Stanford emphasizing reliability. Dario Amodei, he says here in a blog a few months ago that I actually think the most challenging thing about AI agent is making sure they are safe, reliable, and predictable. Again, predictability is also a component of reliability. And this is another quote I will cite. I know that this is what's holding it up. It's not the capabilities of the model. It's getting to the point where we are assured that we can release something like this with confidence, and it will be reliably do what people want it to do, and many others. So actually, this is very similar with the software systems. Everyone here probably develops software systems. And you know that in many cases, prototyping a feature, demoing a feature is easy. What is hard, taking this feature to production, right? You know, it's between 10 to 50 times requires more resources, time, to take a feature from prototyping to production than prototyping that feature. And when you are asking yourself, what does it mean to prototype the feature? It's really actually to make it reliable, right? And what does entice, what does productization means actually if you go down to what you need to do? You do testing, debugging, compliance and governance, deployment, observability, right? So testing, right? A software system consists of many components. Depends on what levels you are looking. Libraries, object, functions, whatever. And each component actually has a clear specification. It's an interface. How it interfaces and how it's working with the other components. And the specification defines the expected outputs given an input. So testing is actually checking that each component satisfies specification. It's not only in software, also in hardware, in many other examples. And debugging is basically in the, the system doesn't work end to end. It's identifying the component and the code which violates the specification. Fix problem by changing this problematic code, and you repeat, you iterate until the entire end-to-end system is going to pass all the tests. Okay? Now, again, with software systems, again, you know that, and we all know that, again, productizing a feature is hard because of all of these reasons. Now, think about an agentic systems. We are talking all about agentic system today. And I will argue is that it is actually harder, much harder. LLMs are the key components in the agentic systems, but they rarely have clear specification. Hard to know even when the error occurs. Also, assuming that you know that you have a bug, then debugging them is hard because they are a black box. The software, it's a white box. You can go down and you can debug, you can identify the lines of code which causes a problem. But here it's not. It's very hard, right? It's like debugging this kind of system is akin you have a black box. You have only your program. You cannot peer inside it, right? You just basically change the input, get the output, and somehow you have to figure out what is going wrong, what problem it says the program has. So next I'm going to talk about two projects we had at Berkeley that tries to help a little bit in building more reliable AI systems. The first is LMArena, and the second one is MAST. And the first LMArena is about testing and evaluating large language models in the wild. In particular, it's about human evaluation for LLMs. So why do you care? Why do you care about humans? Well, you care because the most successful AI applications have a human in the loop, right? If you think about code assistants, customer support applications, in general, chatbots, all of them, they have a human in the loop. So therefore, the humans, understanding how the humans interact with these systems matters. It's important. And what drives a human preference? There are two things: substance, accuracy, factuality, and style, right? How the output looks like. And let me make a point of that. We always talk about the substance, and we are engineers and so forth to some degree, so we care about the substance, the accuracy of the answer and so forth. But style matters. Think about the presentation. You've seen a lot of presentations. Hopefully all of them are amazing. But you work through boring presentations, right? About your text, you know, the presenter maybe is boring, is tired, and so forth. Everyone is tired, right? And you have the same content. Now, a much more engaging presentation, higher energy, you know, more picture animations. The point is, although you have the same context, you are going to retain much more information from the second presentation. The same is like interacting with your computer. You know, you can do almost everything from an alphanumeric terminal. However, you are going to be much more productive and so forth if you are going to do the same things through a Windows system, at least for most of us, right? So in some sense, the style about how you are going to interact with the system is determined also how reliable is this interaction. And we know that from other systems, right? This is what we call UX, right? It's extremely important. My point, this is also obviously it's very important when you are going to interact with the chatbots and things like that. And you need to understand what are the human's preferences here. So this is LMArena, which was formerly known as Chatbot Arena. And basically, this is about, you know, you have, it's a website, you can go right now, and you can ask a question, what is AI reliability, and you can get two answers from two randomized large language models, okay? And then you can vote which answers is better. So this is the wild. People ask their questions, so they are real questions from real people, and they are voting on the answer to their questions if they feel confident and they want. And we take all this data, and we compute a rating, and we have a leaderboard of this model, so using this Bradley-Terry model. And we also have different categories, like math, you know, coding, hard prompts, English, and things like that. And we have not only for text, but we have for video, images, and so forth, and web development, and many more tasks. And we study this kind of, then based on this data, this kind of human preferences. And not only studies what humans prefer, but quantify that. And here are some early results. So basically here what you can see is how different attributes of the outputs influence the humans in saying this answer is better. And here is the length of the answer, markdown, different attributes of the markdown, whether it's a list, markdown header, markdown bold. And if you look at all of those, then, and you compute the regression coefficient, the largest is for the length. Now, this in general is because the longer outputs also contains more information. Sometimes they are also more verbose, but also contain more information. If you forget about the length, then the next one is a markdown list. So markdown list, like you can imagine that you have a list, you present the output in an order list about the main points of the output, is more important than just having the header or boldify using bold text. Subsequently, we did another study, and we added more attributes here. The answer length is still at the top, but the other one, because there are a lot of questions actually a few months ago, emoji. How much emoji is going to impact your preference of the user, saying it's a better answer, everything being equal. So surprisingly, it turns out that this emoji count is negatively correlated. The intuition here is that if you have a few emojis in the answer, that's fine. But if you are going overboard and you are going to have a lot of emoji, people will mostly, well, on the average, will not like it. I think in terms of impact, LMArena is very popular. We have over 250 million conversations. We evaluate over 700 models, 7 million or more monthly active users, and over 5 million votes every month. And it's used today by many model providers, top model providers, to test their models before they are releasing. For instance, Nano Banana, the recent model from Google, was first available on LMArena for people to try it. Of course, it was under anonymized name. Okay. So the second part is going to be about, okay, so this is kind of, we have some evaluation. The second part is going to be about agent systems. And it's about failures in agent systems and how to taxonomize these failures. So what is agent systems, right? An agent, like we know, is basically an LLM using a tool, like web search. A multi-agent system, like the name implies, is a system which you have multiple agents collaborating to solve a task, right, and use different tools. Here is kind of an example you'll hear often when people talk about multi-agent systems, in which you want to build a software application, a program, and then you are going to have each agent assign different roles, like a CO saying what is the task, a CPO is saying, providing like the equivalent of product requirement documents, and then the engineering implementing it and checking it and so forth. So we try to look at quite a few agentic frameworks on quite a few benchmarks. And here is just a little bit of data to give you a taste. But the TLDR here is that with yellow, you can see the failures, blue, success. So most of the cases, these agents on these benchmarks fail over 50% of the time. So obvious natural question is, why do multi-agent systems fail, right? So this is what we try to systematically identify to this failure, to classify them and analyze them. And MAST is standing for multi-agent systems taxonomy, failure taxonomy. How did we do it? We manually inspected 150 traces from these runs. And then we develop an automatic pipeline based on LLM as a judge to evaluate these traces. And we evaluated over 1,000 traces. The agreement between the human evaluations of these 150 traces and our pipeline is 95%, pretty high. And we look at 7 agentic frameworks. And this is our taxonomy. On each kind of big row, specification, interagent misalignment, task verification. These are categories, big categories of failures. On the vertical, you have all these failures occurs. Before execution, during execution, after the execution, when the results are verified. And then you have subcategories. The first point to notice here is that there is no dominant failure category. The most dominant is around 40%, the least dominant is around 21% or 20%. So let me briefly discuss each of them. Specification issues. So these are things like originate from the system design and poor and ambiguous prompt specification. Like disobeying, and some categories are disobeying task specification, disobeying role specification, step repetition, and conversation loss. You don't provide all the information, and agents are not aware about termination conditions. So here is a very simple examples. Here is the CEO and CPO have to decide, and the CEO has to make a decision about what is going to be built. And the failure here is the CPO doesn't wait for the CEO to make the decision. So he disobeys the role specification because he should act only after the CEO makes the decision and tells it the decision, right? Now, it turns out, because many of us will say, oh, LLMs are the problem. Well, it turns out that, yes, LLMs, the power of the LLMs can be a problem, but it's not the only problem. Like I mentioned, prompt specification and system designs are also issues. For instance, here, if we are going to change a little bit the protocol and we add a explicit step that the CEO should make the decision, right, after the discussion between the CEO and the CPO, the accuracy increases by 9.5%. Okay? So improving the design of your system will improve the performance with the same model. The second category is inter-agent misalignment. And these are things like they can ignore the input. The reasoning action mismatch. So basically they don't do what they are told to do, what they are saying they are going to do, agents. Information withholding, don't provide all the information. Or failure to ask clarification questions. So here is an example. Here you have a supervisor agent asking a phone agent to do an action on an environment, on a tool. Okay, this is Python executor in this figure. And for that, a supervisor is providing the login as a user as the email address of the user. So the phone agent, it provides to the phone agent. The phone agent tries to take the action on the tool, and the tool says, hey, I need you to log in. And it's saying log in, and the username provides a phone number. Now, the phone agent is going to send, okay, this is a credential which are given by supervisor agent, but you notice that the username is an email address. So right here, what you have here is that the phone agent ignores the instructions from the tool to provide the username as a phone number, and is just going to provide as an email address, right? Furthermore, eventually this results in a failure, and eventually the phone agent is providing a failure message also to the supervisor. However, in the failure message, it doesn't say what the actual failure was, okay? So it doesn't say that actually, hey, the username should be the phone number, not the email, okay? So you really need to focus here, it's on protocol design, but also this will not be enough. And it will help. You also need to have the agent to have deep social reasoning abilities, to ask clarification questions if they don't have all the information, to rely all the information to the other agent, and so forth. Finally, task verification. And this is our failure related to quality control, to verify the outcome of the system. It's premature termination, there are incomplete verification, incorrect verification. Here it's a simple example. You want Ask Agent to design a chess game using the standard notation, right? Like denoting all these kind of squares by letters and number, and then you have a new letter in front which defines what is a piece. And then you have also a verifier, and the verifier say, hey, this looks good to me. However, it turns out that nothing is good. Like, for instance, the program which was created does not follow standard chess notation, the pawns can move backwards, and so forth. Okay? So again, it's total failure of verification. It's not only the program was bad, the verification failed. And here you are talking about chess. There are many, countless programs of chess out there online. Okay? So really you need here things like unit testing and multi-level verification in order to improve reliability of the systems. So MAST annotators, it's on the web. You can use it to feed your own traces from your own agentic systems. And you are going to get a categorization of the failures. And with that, let me conclude. So again, what I argue here is reliability is critical to AI success, and I presented two aspects which I believe help us advance the research agenda to improve reliability of the systems, LMArena and MAST. And obviously, this is just starting. Many challenges ahead. Before you go, some parting thoughts. Again, reliability is important not only in AI, but in every system we rely on. Everything. TV, freezer, car, everything. So it's a staple of the engineering disciplines. Mechanical engineering, software engineering, aeronautics, and so forth. And again, reliability in AI is going to be as important if you are going to depend on AI for critical tasks. And it's going to, achieving it is going to be even more difficult. And why? Because in all the other disciplines, the key which makes this achieving reliability tractable is specification, right? Because specification helps you to verify whether the system is what it's supposed to do. How do you know the system is doing what it's supposed to do? Well, it satisfies that specification. So you have to have that specification, maybe implicit or explicit. Helps you to debug the system. Decompose the system, different components. Each component is having its own specification, right? This is how you interface between the components. Reuse existing components. If you have a specification, a component which has a specification, you can reuse it in your system easily. And obviously, automated decision making. Because if you can verify the results of your system, right, and you are sure about that verification, now you can let them do automatic decision. You don't have to need to human in the loop. We do have a paper making this kind of arguments, and I think that the main point I want to end up with, obviously we need to learn from other disciplines on how to build reliable AI systems. Reliability is not a problem only specific to AI, it's a problem specific to anything we rely on. Thank you.